Welcome everyone to the November 2021 meeting of the Utah Amateur Radio Club here online. Morris, say hi to the people.
Hi to the people. Just a couple of little things here. In a couple of moments, I hope that we're going to see a slate of candidates that we have for the offices that will be elected next month. And if you are interested in taking a technician, general, or extra class, please send me an email. Those classes will start mid-January, usually the week after the UARC meeting. And there is that list of nominees. And anyway, if you're interested in taking a class, send me an email at my call sign, ad7sr@arrl.net. Back to you, Clint.
Last month you were saying that you might be doing an extra class. Any more on that?
I wish I did, but it continues to depend upon how well we beat this virus down. If we can get to the point where I'm comfortable at having people in my house, then we will have the extra class because we don't want to do that one online. But the technician in general will be online. Here is just the list of candidates. The two open positions that we had that we didn't have any candidates for were the two program chairs. We've gotten 2 volunteers to take those positions. That does not mean that if you're interested in taking those positions or any other, that you should not submit your name to anyone on the board. Our email addresses are on the UARC website. So if you're anxious to be on the board and think that you can contribute something productive, please submit your name.
All right. And the 2 proposed chair people are Mike, KI7MTI, and Jerry Brummett, WJ3RI. So that's who it is. There have been several trips to Leamington after the weekend, I believe. Was it the weekend? No, the week and a half after the last meeting, we put together a pretty good sized work party and managed to do some of the things you're going to see on here. That is, drag the beam to the top of the tower. Things didn't quite still work, so we went down a few days later, almost a week later, and fixed the main issues. Gary, do you want to show us some beauty shots of what's
sure.
going on?
Yeah, can you hear me okay, Clint?
Yes, you're doing fine, and okay, I can see you as well.
This is about 3 or 4 years ago. Morris asked me to get involved in this Leamington HF remote project, so it's been great. It's been up and running for 3.5 years. And let me show my screen here, because this year we did go there about 5 or 6 times and had a bunch of people involved to make some hardware and put up this beam antenna. So that's come to fruition. Last year we were only up there once the whole year. Let's see, I'll share this screen and all right, do you see the new beam antenna there?
Yes, go ahead.
Okay, good. Well, first of all, I'll remind you that to use the HF remote, go to the UARC website and select on the left this HF remote section. So if anybody wants to use it who hasn't, read this on getting started and use it. And these pictures and video that we're showing are available here. This photo album link down here and the specs of the new antenna. But anyway, after you do that, let's see. You'll use RC4 client and bring up the antenna like this. So you can control the radio here, and over on the right side, there's a rotator control. That's what you'll use to control the rotator. So when I click like the 45 degrees, and that green line is showing the current position of the antenna. So it's moving right now physically down at Leamington. So that's how you'll control it yourself. And let's just go to a video that we recorded when we were last there here. And so this is a ASL 2010 log periodic beam covering 20 through 10 meters, all bands, all the 5 bands there, including 17 and 12 and 15. And and it's been used. I think my very first contact here was with New Zealand. So the additional like 6 dB of gain over a dipole is really useful in picking out stations. So that's available as antenna number 3 down there at Leamington now. And let's see, anything else I should mention, Clint? Oh. Can you see that video okay?
You were muted, Clint.
Yeah, okay. Go ahead and show how antennas are selected briefly. And also just do a brief mention on which antenna should be used when.
All right, so let's reconnect to the remote in real time. And let's see.
Hit a double click.
Let's try it. Here we go. So yeah, over here on the left, there's antenna number 1 is the G5RV. It's been there a long time. Antenna number 2 is installed in June 2019. That's an end-fed half wave that's resonant on the 160 meter band. So it can be used on 160, 80, and 40, and as well as the 60 meter band. And then this is the log periodic beam that just got up and running this year, that the rotator affects. So it's, like I say, useful on 20, 17, 15, 12, and 10 meters. I think that first contact with New Zealand was on the 10 meter band. It happened to be open. And then I had a contact with let's see, I think it was down in South America, and then chatted with a guy in Austria in Europe. So this, and it's very useful for those bands, like enter the frequency and change the rotation there. So that's about it. Did you want to show your video, Chuck, or anything else? Is that about enough?
Yeah, I can do that.
You may be wondering how it is that we got a tower on top of a tower. Well, that required a lot of pulling and some rope. But the bigger challenge was how to stand up a tower on a tower. And that is how you do it. Go ahead, Chuck.
Okay, let's see if I can turn the volume down. I found that. Full screen here. So yeah, a lot of ropes to get it up to where it is right there, and brute force, and a prior trip to install a sky hook so that we could use this winch. And so now it takes one person to raise the antenna. That's the guy pushing the button for the winch. So here we go. And it only takes about a minute to get it up.
Might mention what that noise is.
That's the winch. So.
As heard from 7,500 feet away.
Yeah.
Yeah, this is actually Bruce Faraday's winch. It's a 2,000-pound Harbor Freight DC-powered winch bolted to the skyhook, which you've seen in previous UARC meetings.
Where Clint is standing on the platform at 62 feet, and I'm directly below. So.
Right. Now, to stand this up, we actually set up some temporary guy wires, so that. But it also turned out that it was a bit windier than we liked, but it really wasn't too bad. I think we had gusts of maybe 15 miles an hour, but with all the shading of the tower, being on the leeward side and on all the horns up there, it didn't feel like it was going to grab it away from us particularly. Although it did make it kind of interesting to pull it up because it wanted a cartwheel and turn other directions.
So this little droopy coax here goes up to the G5RV. And so that was it. It only took 4 trips in all summer to get that up there.
Right. In the meantime, we stored the antenna on the roof of the building. So I think it took, what, 3, put it on the roof and take it off again before we finally got it on the tower.
Yeah.
At least 3.
Yeah, the only time we didn't take it off the roof was the early August when we installed the skyhook.
Yeah. Since we went down there knowing we wouldn't be putting the antenna up. But anyway, if you want to use the Leamington station, let's see, make sure you talk to our club president, Morris, and ask him for permission to use it. But of course, he will also insist that you read the instructions that are on the Utah Amateur Radio Club webpage about using it. There's a manual there. Let me bring up the screen to show you how to get there. Let's see, there it is. So over here at HF remotes. Let's see, let me move this screen off here. At HF remotes, this is where we were before. And read the quick reference guide and the station manual, and then talk to Morris by email. Of course, to be on HF, you really should have the appropriate license. Now that, I don't know, Morris, now that 10 meters is opening, are you thinking of letting technicians maybe using the station, or is it still generals, or what?
I think we're still going to limit them to general, because a technician could use it, could say they were just going to use it down in the bottom part of 10 meters where they're authorized to use it, and then use it on any other part, and that would not be legal. And so we'll just keep them legal and not allow them to use it.
Okay. Well, an incentive to
besides
upgrade.
that, it gives them a good incentive to get their general license.
Right. Okay. So if you're a UARC member in good standing and you have general or something or higher, then you are absolutely welcome to use the station down there remotely. All right. Any other business of which we should be aware before we carry on with the topic?
Not for me.
Okay. Let's see here. Okay. I'm just trying to figure out why my Zoom video is misbehaving. Anyway, all right. This evening, we have a presentation. Unfortunately, the gentleman who did the presentation was on a different schedule than he anticipated. So this had to be recorded a bit earlier, but so hopefully I got the questions. And I will switch to that now. We have with us this evening Larry Labayen. Is that how you say it?
Yes, Labayen.
Labayen. Okay, I'll try to remember that. We have with us today Larry Labayen, and tell us who you're with and what your job is.
Yes, my name is Larry Labayen. I'm with Lincole, XIT Grounding. We, as a company, specialize in lightning protection system inspection design together with VFC. And then our niche as a company is also grounding system design, not only for just about any applications that are out there, the radio sites on the mountaintop or the cellular sites, utilities and the military installations. We also do grounding system designs for the substations. So we are focused on grounding, bonding, and electrical protection as a whole as a company.
I see. So, I take it your projects are really big projects, like entire buildings and everything else. I mean, everything big and small.
Yes, they are from a power generation plant down to a single cell site up in the mountaintop, or an emergency relay station up in the mountaintop, or in the middle of downtown, in anywhere, so it's all over the place.
Okay, maybe this is a question for later, but in a nutshell, maybe you'll cover this. What's the biggest nightmare situation where somebody says, we want a good ground system, and here it is, try to do something? What's
The biggest nightmare would always be up in the mountaintop where there's nothing but rocks.
I see.
That is the biggest nightmare. But there are solutions out there, and I hope I'll be able to cover that later.
Look forward to hearing about it. Well, I guess you have a presentation, so unless if you're ready to go, let's do it.
Sure. Here you go. Let's see.
Okay, it's
There you go.
there we are. We're good.
All right. So lighting protection in the radio telecommunications industry. To go about with this, I'm going to go through and hopefully just cover a little bit about what standards are out there what standards are being used out there for lightning protection as a whole in general, and also cover the basics of lightning. And then we'll delve into a little bit of what you're looking for as far as the effects of lightning into your radio communication systems, or any systems at that. And then hopefully I'll be able to present some solutions that might work out for you, or trigger some ideas from within your own installation, what you may have to do to help you protect your system from the effects of lightning as a whole. So let's go through it. So lightning, how does it form? What is it? What is lightning protection? Do I need lightning protection? A little bit of grounding basics. We can cover that. How does the telecommunication industry deal with lightning as a whole? So here's a little bit of a demonstration. The basics. So as we know, every time there's a cloud that starts forming up in the air, there's always a chance, especially during storms, there's always a chance that lightning would strike. Now the question is, how does it form? Essentially, the basic idea is you've got electrons that would start flowing, collecting up in the lower parts of the clouds, and the cloud on its own will have negative and positive electrons. Depending on where the charges are in that cloud, you may end up forming enough charge so that you'll have a step leader, which would start coming down from the cloud, and a streamer, which would start coming up from the ground. Sooner or later, those two would meet, and that's when lightning occurs. Basically, that's when the discharge actually occurs, when both of the streamer and the step leader meet up in the middle.
Is there any current flow or any signs that that's about to happen, even if they don't complete?
Yeah, normally you'll have basically a lightning discharge is basically nothing more than a big electrostatic discharge. So before something happens, if you're really in the middle of that strike, just about before it happens, a lot of people are saying their hairs would start standing up. That's basically kind of like what static is. It's a big electrostatic discharge. So when you start feeling that, that's when you can start saying, oh, something's going to start hitting us. So take cover.
Are the step leader or the streamer ever visible, or only under best conditions?
They're normally not visible in the human eye. It happens so fast that a lot of times the only time that a lot of the high-speed cameras can get it is during when it occurs. So they're using high-speed camera. On our end, on our visual acuity, we basically would end up just seeing a flash at that point. That's when both the step leader and the streamer basically meet. And then there's a big discharge. As far as the amount of discharge, it's a lot of current and a lot of voltage. So we'll go through that later. So as we see, it's basically the flow of electrons is from negative down to ground. There are some instances where an opposite would occur, but that's a very unlikely event. most likely event is always a negative to a positive discharge from cloud to ground. Now, you'd wonder sometimes, why are there cloud to cloud discharge? That's because some of the clouds would have more positive electrons than the ground. So it'll end up discharging onto itself, onto the next cloud over. That's when the cloud to cloud occurs. Here you go. These are some of the observed potential current per stroke. So 18 kiloamps of current that will be flowing down that path is what's being measured. A duration of 45 microseconds. So if you think about it, it's basically all the way from a discharge, the moment it strikes to the discharge point, it's when it settles down to zero. It's about 45 microseconds. And a median rise, the instant the lightning connects, it's basically like turning on a switch. That instant is about 1.8 microseconds. Now, there are some news. That's because not all lightning occurs the same. This is kind of like an average or common occurrence. But there are some lightning that has a slightly shorter, slightly longer rise time, and some of them are slightly shorter rise time. But the key is, if there is an immediate transient that occurs and a slow discharge that happens after that. So it's almost like turning on, shorting a discharge capacitor, charged up capacitors, discharging it. So that's what happens. Here are some of the statistics on lightning that's been presented by State Farm. So there has been 756 lightning deaths between 1990 and 2003, and 1.7 billion lightning insurance claims between 92 and 96. Yearly loss at about 332 million. So, and the point here I'm making here is, we know lightning occurs, we know there are fatalities, but the insurance companies are now focusing a lot more on lightning because of the insurance claims that's occurring. So there is a rise of companies starting to look into how to best protect their facilities and how to protect personnel and equipment in their current during lightning strikes. And if you look at this chart as well, or this map, it shows pretty much how they're ranked, and it pretty much correlates with the lightning events throughout the years in those certain areas. So I would say you guys are in Utah, so that would be, in your state, that would be like 22, ranked 22. And I think lightning occurrence there is not as bad compared to Texas or Florida, but yet there are fatalities, or there are buildings that are damaged, or equipment getting damaged. It only takes one strike. Even if it occurs once and you get struck, that's it for your equipment or your structure.
Yeah, where I used to work, we took a direct hit on one of our communications towers, and we were not as good at making sure the customer that had just installed the equipment had everything grounded and protected, and every piece of their equipment was destroyed, and only some of ours was.
Oh yeah, so yeah, that's one of the things that we always respond to whenever people call us in for looking at an event that may have happened on their site, and would end up having to come out there and find just the basic stuff that you can do that can help improve your site from being more resilient from lightning. So the basic purpose of a lightning protection system is to basically intercept the lightning. That's basically it. Lightning will do whatever it wants to do. If you don't have a lightning protection system, you're more exposed. But if you do have it, you're somewhat protecting yourself by directing that lightning current to a desired path when you have a lightning protection system. It just minimizes the amount of damage and minimizes the potential of having some some fault or damage into your system, or even fatality into the site. So what are the traditional components in a system? Basically, there's the air terminal or the lightning rod, which most people know of it as the lightning rod. The conductors that interconnect all these rods together, and the basic is the grounding electrode. So basically, you're giving that lightning energy a path to Earth, because basically we're basically, the air is it's basically like a capacitor. You have the negative ions on the cloud, positive electrons on the cloud, and positive electrons on ground. And in between is the insulation, which is the air, and you want to give that potential back to Earth. Basically, it wants to return back to Earth. So by providing the air terminal, the conductor, and grounding electrodes, you're providing that path for lightning. So what are the basics? NFPA 780, which is the basic standard for lightning protection system in the US, requires protecting an instrument or a structure. Protection can be achieved by having an air terminal that's at least 10 inches above the object being protected. The conductors, there's special conductors that are used for lightning protection systems, but NFPA do allow the usage of regular conductors of a certain gauge based on the height of the structure or the height of the air terminal, where it's placed relative to the height. It could be copper or copper-clad aluminum. Grounding electrodes, we all are familiar with grounding electrodes for sure. We have the driven rods, the ring, the radial. I can cover that later bit if you have any questions. A plate electrode, it's nothing more than just a 1x1 piece of copper plate that's buried, or a concrete encased electrode. Again, that could be, or what they also known as a UFR ground. A concrete encased electrode is something that's, because it's buried, and it can maintain a certain amount of moisture around the metal. There is a sense of a good grounding electrode out of it, because it can maintain a certain amount of moisture around that metal. But the only trouble with concrete encased electrode is when lightning strikes something and you direct that energy through the concrete encased electrode, sometimes the concrete would superheat itself, that it'll just basically crack. So, it's approved as a method, but it's something that I myself personally do not want to rely on. Therefore, I prefer having some driven rods or radials on top. To add to that.
I guess do you subscribe to the opinion of the more paths to ground, even if you didn't want to use a UFR ground, for example, the more paths, the better? Or,
yes, I subscribe to that.
As long as they don't take you through something critical, I suppose. You don't do something silly like run your conductors through the same cable race as sensitive signal cables, I guess.
Absolutely. That's one of the things that IEEE actually recommends. You try to keep them away from any signal cables or low voltage cables that you may have, primarily because of induction or capacitive coupling that might occur between the cables. So some of the concepts of the lightning protection system. Basically, what they're saying, there's anything under the radius of 150 feet, any objects underneath that, which the picture shows, is what they refer to as zone of protection. It's basically a zone where lightning is very less likely to get to reach. So here you are, an example of a pole with an air terminal at the very top, and we put a radius of 150 feet ball next to it, and anything below it is basically protected. So if you have a shack that is butt next to that structure, and it's within that shadow of a 150-foot ball, you are pretty much considered safe from a direct lightning strike. Now that 150-foot ball changes when the norm is 150-foot ball, but if you're in installation as such where you have explosives or chemical plants, that 150-foot ball is reduced to 100. I think it's 100 or 75-foot ball. The only reason why they're doing that is there are some discharges which are low enough in current, but yet enough. You may not see an actual strike, but it's enough to actually ignite the fumes or ignite the explosives. So they'd like to actually discharge the potential earlier than normal. So that's the main reason behind that.
I don't know if this would be a good time to bring it up, but I heard someone once tell me that Ben Franklin went to the grave never having seen lightning hit a lightning rod, but yet he knew they worked. But I mean, so that brings up the question: can lightning rods discourage step leaders from forming, or are they mainly just to
attract it?
Phase they are? Yeah. Well, I don't know. I don't think lightning rods attract lightning. I think they just tell it. I think they guide it where you want it to go, and not where it wants to go.
Yeah, there are two train of thoughts in the industry. One train of thought out there is that you've got some of the dissipators that they call dissipators, which basically the idea is their concept is that you put enough electrons around a dissipator. So it's basically an air terminal, a single air terminal with like a ball of
I've seen that on broadcast sites.
Spikes, right? That's what they call the dissipators. The idea on that one is you put enough electrons around there that you create a weak link between a leader and a leader all without creating an actual connection. That's the concept. You're sort of slowly discharging the clouds nearby. That concept is being used out there, but that is not recognized much by NFPA.
I take it that falls in the same category as the polonium doped, the ones that supposedly ionize the air locally with a low level radioactive.
Right.
Yeah.
Right. So it's hard to prove. That's the thing. All of this.
Yeah. How do you prove that lightning didn't hit you because
correct.
It was there?
There's no way of proof. I mean, it's very difficult to prove. But however, there are what you call an ESE head, early streamer emissions type head. The concept on that one is as the electric field develops around the surrounding area, it's actually an active device. Well, sort of active, passive, but what it is there's an inductor and there is a capacitor. What happens is as the electric field starts building up around the area, it starts feeding that capacitor. So therefore the tip will have a higher voltage. Once the tip's higher voltage, because it's of a higher voltage, essentially you've been pulling more and more static charge on top of that tip. What its intent is similar to what the dissipator's concept was, but it's proven that it's able to discharge a leader earlier than a regular air terminal, just a passive air terminal. So which means on the ESE head, they're able to say, we have a larger zone of protection with an ESE head because it's able to reach further. Now, whether or not it's going to be a stronger discharge or a smaller amount of discharge, which you don't see, is completely beyond me at the moment. But all I know is they actually do an actual test in Spain, where they actually put it underneath a very high voltage plate where they do their testing for any air terminals. And they've actually recorded it that it actually reaches out to the negative electrons sooner than a traditional air terminal. So that it's a product out there. It's not recognized by NFPA. It's recognized, however, in Europe as a product.
Interesting. Okay.
Yeah.
So is it more? Do they believe it prevents lightning, or just simply makes it go elsewhere?
They believe it's basically acting like a traditional to attract those electrons and dissipate it from the ground.
Oh,
so
okay.
So
Yeah.
it might be a weak connection or it may be a strong connection. So one of those two.
Yeah, clearly it probably doesn't change the number of electrons accumulating in the cloud or whatever.
Right.
But if I guess if it doesn't hit you, then you've done your job.
Yes. So placement of air terminals. So this is kind of like a quick and easy way of looking at how air terminals are placed. So again, with a zone of protection concept being used, this is the method that's being used on designing a lightning protection system for any buildings out there. And this is basically recommended under the NFPA 780 standard. So essentially, anywhere the ball touches and anything above below it is basically protected. So if you notice on this diagram, you'll see that some parts of the building are actually protected because the ball is basically kind of riding on the tips of those air terminals. If you notice on the left, on the very first ball, it's kind of touching the edge of the building. I did that on purpose. In reality, they consider that even if that first air terminal is actually within 2 feet of the building, they consider that as to be protected. I guess the whole reason it's still close enough that the chances are higher probability is that the air terminal would be struck first before the building. Okay, so this is the basis of how they do their design. So here's an example of a tower. Again, using 150 foot sphere. As mentioned earlier, areas where the ball touches is basically underneath that ball is protected. So on this example, anything above 150 feet is pretty much exposed to any lightning strike. So antennas that are up there, some communications company or actually put additional protection on their antenna. Some communications company, they don't. They basically consider the antenna as a strike termination. They just double up on their protection on the conductor coming down. So it all depends on the application. It all depends on what kind of risks the telecommunication companies want to take with regard to their antenna. Yeah. Majority of the time, they'll have an air terminal at the very top and always position their antennas lower than the air terminal.
Okay, so in this particular drawing, people say, well, I just thought a tower would protect people on the ground. So is there an air terminal not on the top of the tower or what? You know, I guess the question people ask is, why isn't there a ball bouncing on top of the tower?
Oh, you mean the rolling sphere?
Yes.
Oh, yeah, it's because it's pretty high up. The moment it's almost vertical, they consider that to be within the strike zone. Okay,
so yeah. that makes sense actually.
Yeah.
So yeah. if it's way taller than the 150-foot radius,
those are within the.
Right. Okay, that makes sense.
You are within the strike zone.
Okay.
So antennas that are beyond 150 feet, they would still put air terminals at the very top, because in most cases lightning hits the very top. But the sides, they would put probably a cable coming down or put an arm with an air terminal next to an antenna above and below. So those are things that they do. I know you'd start asking how does it impact their antenna patterns and all that stuff. They have to consider all of that.
Well, I can tell you from personal experience, we've lost a repeater antenna on a tower, and And we would much prefer have a disturbed pattern from an air terminal than no antenna at all.
That's right. I agree. So yeah, sometimes they'll just put a point coming out on the above the antenna and a point coming out below the antenna. So sometimes that's enough.
Yeah. Okay.
Yeah. So here's a proof: lightning does not always strike the tallest object. So you can see it hit the platform of this space shuttle instead of the air terminal that they have, that big white air terminal on the very top that you see. That's very prominent. A lot of their pictures shows that it's always being struck, but this one photo, for some reason, it avoided it. So placement of air terminals. So the standard requires that it be placed about 20 feet from each other if the air terminal height is 10-inch to 24-inch tall above the object being protected. If it's higher than 24-inch tall, you can space them out at 25 feet apart. Again, imagine the sphere or the ball rolling between those 2 points. The idea is you want to have at least 10 inches separation between the apex of the roof, or the surface of the roof, and the bottom of that ball. So that's kind of like a general a rule that they use for installing air terminals, so that you get good protection. They also say that 24 feet from the edges of the roof or any equipment, 2 feet from those edges is okay. Okay. Is lightning AC or DC? Well, we pretty much know it's DC. Most of the energy is DC. Fast rise time generates a significant amount of RF energy. That's basically where it starts, as transients. That's where the RF energy starts.
Do you know roughly the frequency concentration of the RF portion? I've heard it said that it's in the hundreds of kilohertz range.
Well, if you just take the frequency of 1.8 microseconds, or I use 1 microsecond, it goes up to 10 megahertz.
Yeah, that alone indicates what, a few hundred kilohertz to a meg, roughly.
Yeah. So it's pretty high, to be honest, and it's hard to imagine, but it has that component. As far as the amount of energy, it's hard to say what the rise time would be of the system. It all depends on the path to Earth as well. So the rise time can be slower, and then you'll have less energy on certain areas. So a lot of that it's very variable. So down conductors are basically the conductors that you have that takes it from the air terminal down to path to Earth. So one of the things that the NFPA requires is you do not want to have any sharp bends, kind of like the coax. I know that I was a high-end radio operator in college too, so I know a little bit of some of the rule of thumbs that they have. So it's kind of like coax, bending coax. You don't want to have it, what was that, 8 times or 10 times its radius. You don't want to have it. On this one, the down conductor, they require, as a standard, at least 8-inch radius. So you want to bend it at 8. You don't want to minimize bends and have. If you do, you should have at least an 8-inch radius. And you don't want to have it to be less than 90 degrees. So you don't want to have like a U shape or a V shape conductor path or grounding conductor. Because essentially any bend or any sharp turns are basically high impedance points for that current. As we say, it's because it's pretty much a steep transient. You'd like to get it out and dissipated to Earth as soon as possible. Otherwise, you'll have a high energy left on that conductor, and potentially any equipment you have there may get damaged. So these are very important rules that the NFPA has established.
Maybe you'll cover this in, but I guess you do not want that ground down conductor anywhere near any other conductors if you can avoid it.
Yes, it's good that you brought that up. I don't think I covered it here, but NFPA 780 has a requirement of an X amount of distance depending on the height where the air terminal is. But because that could vary. UL 96, which is another is a lightning protection standard that most industries used for certifying the lightning protection systems installed, just basically standardized on a 6-foot rule. So anything that's within 6 feet, you'd like to keep it away from that conductor whenever possible. But essentially, the key thing there is because they don't want to have a side flash that might occur between the conductors. But if it's noise that you're concerned about, 6 feet is more than enough, and it all depends on how much current you're going to have there.
Plus 18 kiloamps and a microsecond rise time will generate one heck of a magnetic field that'll cross everything else. I've actually had an argument with somebody who insisted on running, for purposes of appearance, running the ground down conductor through metal conduit that was insulated from the ground wire.
Oh, bad move.
Tell us why. Tell us why.
Because what you got now is mutual impedances or mutual, how should I say, inductance that would occur. So now what you happen if you don't ground the conduit, the metallic conduit, ferrous conduit to the conductor, you'll have opposing currents that would occur and basically opposing fields, which would mean, again, high impedance. So you're basically making it as a choke. So a big no-no.
Yeah, I mean, there's that old trick where you can drop a neodymium magnet through a piece of copper tubing and it just flutters its way down, takes a few seconds to go all the way through because of eddy currents induced. The other thing too, I've heard a rookie electrician make the mistake of running phase A, B, and C through individual metal conduits and wondering why the conduit got really hot.
Oh, God. Yeah, that explains that.
For the same reason, for exactly the same reason.
Exact reason, yes, exactly. So NFPA 780 does require you to bond any down conductors or any conductor through any piece of ferrous material on both ends. So bond it to that same conductor. Not only NFPA 780, but also the NEC requires that as well for grounding conductor. But if it's phase wires together with ground, they don't require it. If it's only a grounding conductor, especially for grounding electrode, they require it.
Okay,
so that's consistent throughout the standard.
All right,
good question. So materials for lightning protection. It shall be copper alloys. The main reason here is they want to make sure that it doesn't have corrosion, trying to protect corrosion on any of the connections or any of the lightning protection system. No copper on aluminum or iron or galvanized surface. Copper will basically make aluminum disappear or rust anything iron or galvanized. So a lot of the lighting protection systems that are being installed now are mostly made of aluminum because they're pretty much neutral relative to most of the materials that are out there that are being used in the roof.
Maybe I'll get to this, but typically you do have to ground a galvanized structure with something. Correct. So I know there's CAD welding, but I guess are you talking about making in contact, or if you're connecting them, bonding them in a certain acceptable way, like
when you're running, for example, if you're running all these conductors up on the roof and you have a copper roofing system, and you put aluminum system up there, then your aluminum system would basically get corroded. So you need to match it. And then on the reverse, if you have galvanized corrugated material for your roofing system, you put copper system on the roof. Through the years, you're going to start rusting away your galvanized sheets.
So I take it it's not enough to put something like no-locks, or is there some interstitial like cadmium plated material that you would use, or interstitial material?
Different material, basically. Primarily, this whole requirement centers around for anything where both materials are exposed to moisture all the time. So exterior. On the interior, to answer your point, if it's a galvanized steel, you can bond galvanized steel to to copper when and if it's in the interior where moisture is less likely to occur. When it's outside, exterior, it's always best not to do so. But if you do so, you can isolate. I mean, keep them isolated somehow. And exothermic welding, that bond itself is is compatible as far as materials are concerned.
Oh, like CAD welds. Okay,
Yeah.
yeah.
Mm-hmm. Yep. And there are other plates out there that the lighting protection industry uses. They call bimetallic connections. It's basically an interfacing metal in between aluminum and copper, or copper, aluminum, and galvanized steel, where it makes them compatible. But what that does, excuse me, what that does is basically creates that bridge. But when moisture occurs in there, the bridge between aluminum and that bimetallic would not be enough to have a difference in potential, galvanic potential, where there would be a corrosion that would occur, and the bridge between the bimetallic metal and copper or galvanized steel, the same thing. So it's all about the galvanic scale of both materials when it's subjected to an electrolyte like water.
Yeah, I know a lot of hams will ground their towers with not necessarily CAD weld, but like stainless steel bands or just clamps or something like that, and then goop them up as best they can with no loss of equivalence.
Stainless steel, depending on which stainless steel you use, stainless steel are generally compatible with galvanized steel or regular steel. So they're good to go on that one if that's the case.
Like yeah, the most common being, I guess, 316 stainless is the bog standard stainless you find everywhere.
Yeah. And use any stainless fasteners if you can. That'll also improve it further. You know?
So to your knowledge, maybe you can't speak to this, is the standard bog standard 316 stainless good enough if you just do it right?
I believe so. In fact, a lot of times that's what we recommend them use, because what we find out there is a lot of people would use I might say this wrong, chromite coated, or that yellow coated.
Zinc chromate, is that what you're thinking?
Zinc chromate, yeah, zinc chromate, or just a regular zinc type fasteners. Oh, after a while they get corroded really bad.
Yes.
So
it
becomes an issue.
Okay. All right.
All right. For ground terminals, each ground conductor shall be terminated to a grounding electrode that's dedicated to the lightning protection system. So, what are permitted is basically the ground ring. I mentioned earlier, the plate electrode and ground rod. In a typical house, you'd have one grounding electrode that goes to your meter. If you have a lightning protection system, you would say that, okay, I'll just bond it to here, or you have a mast that's next to your electrical box, you just bond it there. That would be fine, but it would be better if you add another one, because what you'd like to do is dissipate that energy as quickly as you can and not rely only on one grounding electrode. That's essentially what they're trying to say here, is that the more path to Earth that you can provide that air terminal, you'll divide that current to a smaller and smaller level, and therefore having smaller voltages that would occur on the ground potentials. So that's kind of the idea. Concept.
I guess a scoop of Earth can only dissipate so much power, so you spread it out as many scoops of Earth as you can.
Exactly. You pretty much overwhelm that area of the Earth when you have an energy in there. That's pretty much it. It saturates it. That's it. Once it's saturated, it can only do so much.
Now, I've read many years ago that if you do have, say, a tower or somewhere where you're worried about grounding, if you don't want vegetation, you dump copper sulfate, but maybe magnesium sulfate in the ground, which is just Epsom salt, to help improve on poor soils like we have around here. Is that something you've generally heard or you recommend?
Well, a few things with the soil. With the soil, the only Primarily, the soil gets the low resistivity from the electrolytes or salts that it has. So that's pretty much what it requires. So by putting magnesium sulfate, yes, you do, but you be careful with whatever metal that you put on there. That make sure that it'll last, because now you're putting something in there that's basically salt.
Right, and I've observed that copper-clad steel ground rods become just steel ground rods eventually.
Yeah, or sometimes what we've seen, you'll have the copper clad without the steel in the middle. We've seen that as well.
Oh wow! Okay.
So it depends. So it's interesting. Grounding is interesting as a whole. You need it, but then again, the rod will corrode after a while.
Yeah, the way I would prefer to put in ground rods is I guess they don't work for a year or two, but attach a garden hose to a piece of 10-foot piece of pipe and let it drill its way down and let the soil go around it. But because I've had mixed results with copper plated steel rods, or the galvanized ground rods that they also sell, which I don't know that I'd even trust.
Right. Some companies out there are using stainless steel rods, but it's a very expensive approach.
Yes, sounds like it.
Yeah. Bonding. So electric bonding is a key thing here in the lightning protection system, and also communications. You pointed out earlier, you cited the example of your site where your equipment took a little bit of damage compared relative to the other group that's sharing that site, which took a lot more damage. And I have a feeling the primary difference is the bonding and the grounding of your equipment. So the idea there of bonding all the electrodes together. So you may have bonding all the electrodes, bonding all the equipment together in one common point is to basically minimize the potential differences between every point within the system or within the site. With that amount of current that's flowing through the grounding system, you are bound to have a difference in potential, even if you say, I'm connected with a conductor. A conductor has resistance. It has impedance relative to the length. So as it goes longer between the beginning and the end, depending on the transient or the amount of current, you may have a potential that's more than what you desire or more than enough to actually damage an equipment. So bonding is the key thing that's being enforced within the lightning protection system as another way of minimizing loss or minimizing loss in the equipment or even fatality. So if in a typical home, I'm going to think of a typical home, we have a ground rod. The new NEC, the NEC requirements now require that all telecom equipment or utilities coming into the home be bonded together at a single point. Now think about if you have your telco, your cable, let's see what else you have, telco, cable, and the electric bonded together. And that's primarily because the telco and the cable system can actually impose a certain voltage that's undesired into their system that may end up in your house, which you don't want. And now you've got it connected straight into your cable box or into your computer. Computer's connected to your electrical system.
And you hear humming all your speakers and everything else, yeah.
Besides that, you'll end up having a potential coming in from the cable operators that will discharge through your grounding electrode. Guess what's in between your equipment?
Yes. Yeah, that kind of brings to mind, I think we talked about this before, was you have the ham shack on the east side of the house and the service entries on the west side of the house. I know of some people who will just run big, heavy wires between the two, which is more or less what I think should be done. But other ones want to keep the systems separate as possible. And I don't know if I can convince people that when lightning hits your antenna, it'll go through your house, through the equipment to get to the service entrance if it has to.
Oh, that is an absolute no-no in the telecom industry. You need to have a common grounding system.
Yeah, I take it you're referring to the ring ground that you referred to.
A ring ground, or even that one that you described, even just connect between the east and the west location with a heavy gauge wire bare.
And personally, would you have it like go around this side of the house and the other side of the house so that the house is within?
If it's a ring, even better. If it's a ring, it's even better. But if it's a one-sided connection, kind of like a radial, it's better than not having it at all.
Right. And ground loops and hum is another problem that you got to deal with, because if lightning blows the crap out of everything, it doesn't matter.
Yes, that's right.
If it burns your house down, it doesn't matter either. So. Okay.
So a little bit about it. Grounding electrodes of different systems are required to be bonded. That's the key one. This provides a common ground potential. That's essentially what they're doing. Structures exceeding 60 feet in height, the connection of the lightning system and other grounded media shall be in the form of a ground loop. This doesn't mean that it needs to be a ground ring that's buried in the ground. It just needs to be a loop, be it within 12 feet high, within 0 to 12 feet or below grade and above, where all systems are connected together. So you may have a wire just wrapping around the base of your house and everything connects to that, as long as that wire is connected to a grounding electrode as well. But if you're going to do that, you might as well bury that wire, since now by burying that wire, you've improved your grounding system.
So you're talking about burying
tremendously.
Burying a bare wire?
Yes, burying a bare wire.
Okay, I thought I'd clarify that part.
Yeah, perfect. Thank you. Yeah, burying a bare wire directly into the soil. That would be the best way. So any conductor is an inductor. So I show you a radio tower and with some amount of inductance. This is what happens when it gets struck. So if you notice at 150 feet, it could have a very high potential and slowly coming down in level relative to Earth. And even at 0, where the coax would start coming in, there is a potential of having 28 kilovolts of voltage going into the shack. Again, this is all relative to the amount of current that's being pushed, or the amount of voltage, amount of current that's being pushed through the system. This is just an example to show that with this system, with any system at that, you'll always have a potential that would be generated. Even if your ground is at 0, there's always going to be some difference between a distance between the tower and your shack, no matter what. Okay.
So I guess seeing this picture, it reminds me of what I've heard in that. Supposing you have a second-story ham shack, you darn well better take your coax cables all the way to the ground, do the grounding, and then bring them back up, hopefully not parallel with your tower.
All right, so here's what we recommend normally in the industry. If it's on the second level and you have a lightning protection system above you, you have a down conductor and it's close to a coax before it comes into your house. I'm assuming also the antenna is up on the same roof. It comes down. Well, what would normally happen is we would recommend that coax obviously be on the opposite side of the house coming down. But if you can't, try to make it as distant as possible. And then what you do is, before it starts entering the house, you'd like to put an RF kit, basically grounding the outer conductor, the sheath of the coax, and bond that to the down conductor. You don't have to go down; just bond it to the down conductor. Because what you're doing is you're making it in a way you're like a bird on a high wire concept.
Oh, bringing everything up to the same potential.
Correct. It's almost that concept is what you're doing.
Now, what does that do to the other things in the house that might, on the second story, that are connected?
Now, this is where the important information comes into play. All electrical needs to be bonded to the lightning protection system. That common bonding needs to happen. Without that, your system's going to get hit. Okay. Yeah. So the common bonding is required. That common bonding has to happen at ground level, within the 12-foot level, 0 to 12 feet. Okay. It needs to have that common bonding at that level But if your house is well, when you have a lightning protection system, very likely you'll have to have a second path down to earth. So that other side will need to be bonded to the electrical somehow as well. So the idea is you've created a potential equipotential connection for all your grounding system. And you've created that your house to be sort of like a bird on a high wire, and your second level will be somewhat also a bird on a high wire type concept. That is the idea, and that seems to work in the industry, and the industry has been surviving well.
So to clarify, you want your down lead for your ground and your coax to enter as far away as possible, but at the point where they come in the building, they should be bonded. Is that what you said?
Correct. They should be bonded.
Okay.
Correct.
But
and even at the roof level, we also recommend the antenna is bonded to the lightning protection system.
Okay. Well, that part would make sense. Yes.
Yep. So here's some examples of photos that we've gathered through the years of how lightning effects or the lightning effects show. And on the bottom, you can see that foundation is blown away. So certainly, I'm not so sure what really happened on this one, but I have a feeling they probably used UFOR ground as part of that as an issue.
Or maybe it looks like plumbing is part of the ground.
Correct. That might be as well. Yeah. So lightning finds its own path and just no way to control it. All you can do is do your best effort. Is it necessary? Well, the NFPA 780 has a method of doing that. It looks at the building environment, the type of construction, how much the occupancy, the contents, and the lightning stroke consequences. So it basically compares statistically. They've got a math that you follow to tell you whether or not you need it. I have to tell you though, most of the time you need it. Let me put it that way. It's almost like 90% of the time you'll need it. So the assessment is based on expected lightning frequency, areas in the country where there's a lot of lightning strikes, and they're calculated based on the characteristics of the structure. How big of an area does a structure occupy, or how tall is the structure? All of that. Those are being considered. And this is the 2015 to 2019 lightning flash density from let me see, I forgot the name of the company that gives this, but anyway, they're the main ones that actually have all this metering throughout the United States, actually throughout the world too, actually. And if you notice, let me see, Utah, this one. So for every square kilometers, there's probably 1 or 2 strikes per year. But if you look at this, where my pointer is, the blue, that's somewhere in Texas, you got 64 to 96 strikes per square kilometer. So there's quite a bit.
I always thought of as Florida as the lightning capital of the U.S., but clearly that doesn't seem to be the case.
Honestly, when I brought this thing up, when I updated my slide, we had Florida as the highest, and that was like 2000, probably around 2000. So I was just going to bring up that it seems to me that global warming, or whatever this weather phenomenon we're experiencing these days, is shifting all the way around, and it could potential of increasing the area, the lightning strikes throughout the different areas.
Plus, we have remote means of accurately determining the intensity and location of every strike these days anyway. So
absolutely.
Maybe we just know more, but yeah.
That's true. That is very true. We just know more these days, yes. So it's just interesting. So let's touch a little bit about grounding. So what is grounding? It's basically a connection to to Earth. That's what grounding is. What are the components? You got the grounding electrode on your service. So this is a typical one from your pole to your service panel or your meter. You have a supplemental grounding here. You got the required grounding. And this is what we refer to as grounding electrode conductor. This is the one that NEC requires it if it's in ferrous conduit, it be bonded straight to the conduit as well when you're running that. So this is the master ground bar, which they now call, I think, common bonding point. And they also allow an auxiliary grounding electrode. Now, since we touched about common bonding before, this concept right here will not work for any of the radio communication sites at all. So having an auxiliary grounding electrode in your site is a no-no. They need to be bonded to the supplemental grounding and the grounding electrode. So from this slide, referring back to what we were discussing, all those three electrodes need to be bonded together. They can be bonded together at the ground bar, or they can be ground.
Your concern here is being that the auxiliary grounding the path is through the equipment. Is that right?
Yes, the path will be to the equipment, and it may potentially have a different potential, ground potential here than this one. So you'd end up creating a difference in potential within the equipment.
You're advocating a single point ground, as it were, as much as possible.
As much as possible. Yes. So as far as the NEC, they use underground water pipe as a grounding electrode, ground support structure. So basically, I-beams that are embedded. We saw a concrete case early in the ground ring, rod and pipe electrodes, and other listed electrodes like RXIT plate electrodes. So what's different on the lighting protection system side of things, they don't use water pipe as a ground. They don't use metal support as a ground. So the only ones that they recognize are basically the ones that are purposely made as a grounding electrode, like a driven rod or plate or RXIT.
Now, I don't think we've actually mentioned what an XIT electrode is.
Oh, sorry. An XIT electrode is a chemical electrode that what we refer to a electrolytic electrode or chemical electrode that people refer to mostly. What it is, it's basically a self-feeding system where it creates an electrolytic solution at the base, at the very tip of its of the electrode when you bury it. So there's going to be an electrolytic solution. It's almost like basically a salt solution that's down there, which improves conductivity of the surrounding soil. So having that, it'll self-feed the whole system. It draws in the moisture in the air and basically mixes with the calcolites that we have within the electrode and feeds the earth with salt solution. So we know adding salt solution on the soil improves the resistivity, therefore the resistance to earth. That's something that the company had the original copyright. The copyright since expired, but we were Lincole was the main company that started this whole market.
Yeah, I know that one of the main mountaintop sites, Farnsworth Peak around here, they upgraded to electrolyte grounding when they rebuilt the site about 25 years ago. Because prior to that point, if you go to the site today, you just see sheets of copper just laid out on the ground, covered with dirt and rocks in every direction. And those have been there since the 50s when they first light up. Because what do you do on the top of a mountain anyway?
Yeah, you can't do much of anything. Just basically put a ground plane. That's it. So ground resistance is the impedance between the electrode and the remote earth. That's the whole thing. That's the main measure. It's almost like taking an ohmmeter between the rod and going very remote from the rod. So here's the concept right here. So a rod creates a shell or a potential volume whenever it's injected with a certain current or voltage. So each shell would start basically reducing in voltage as it goes further away from the rod, and up to a point where it's zero is basically, the idea is that's the resistance to earth of the rod. So that is, when you see that specification, 25 ohms to ground to earth from the NEC, or you might come across it in some other journals, they require it. That's basically the idea. It's a resistance to remote earth. So where the influence or that shell of that rod is not influencing your measurement. So the noise in electrical systems are either conductive or inductive coupled or capacitively coupled or radiated. So conducted, common returns between circuits or incidental connections. So that could also be, you get a direct lightning strike. Any energy that's on the grounding system is basically conducted. Or you have a short that occurs within the facility, or any noise or any transients that a short creates in your electrical system is conducted throughout the site, and that would impose itself. You got inductive, so any magnetic fields that are induced by current, that would be, again, lightning strikes a down conductor, lightning strikes nearby, it would generate magnetic fields throughout the site or within the site or within the conductor. So anything metallic, you have to assume they're all getting some kind of current. They're all getting induced. So if you think about this, anything and everything within the local area where lightning hits is basically getting induced, and all of these are getting induced in different manners, which means all of them will have their own voltage, transient voltage that may occur, and who knows what they may be. I mean, it depends on how they're all grounded and bonded together. Those levels would change. Capacitive coupling is basically like you discharging onto a doorknob as you reach it during when the weather is really dry. So you can have capacitive coupling. It's a weak coupling, weak type of noise, but sometimes it can still damage an equipment. The radiated noise is basically a resonance that occurred. Again, lightning can go up to a meg. So if you've got anything that's resonant to that lightning transient, that can also create some kind of a noise or some kind of an impact onto your system. So this to say, it's almost like everything under the sun can happen and may happen, because all of these are just so many variables that happen when lightning strikes. Okay. So with when lightning or ESD happens, what are the mitigation? We do lightning protection system, grounding, bonding, surge protective devices. So for radio systems, surge protective devices on the AC line, main AC line that's coming in, and also surge protection at the sub panels, and surge protection at the power strip itself, if possible. The only reason that's the main reason that's actually beneficial is because surge protectors at the main panel has a higher clip voltage, so there's always going to be a let-through voltage that occurs.
Yeah, I know that on Farnworth Peak, surge protectors in power strips are banned because more than once they've come into smoke-filled rooms after a thunderstorm.
Well, there are specific surge protectors for the radio equipment. They are actually rated for that, not the off-the-shelf Kmart.
No. They ban those. They ban those for a good reason. It trips off power circuits, kills equipment. Powered equipment that's fired. Melts things.
Right. So yeah, and then also surge protectors at your coaxial cables or any other signal cables that you may have. Consider those, because so basically, as you go down the panel, you got type 1, type 2, type 3 type 3 surge protectors. The clip voltage is getting lower and lower and lower. So you're essentially, protecting your equipment to exposing it to a lower voltage rather than a higher voltage. even if it's already lower than it actually is when the first clip occurs on the main panel, it might still be too high for your equipment to survive it. Surge protector on the RF cables is very important. The best approach of putting surge protectors, which also doubles up as a good grounding of your coax, is putting a surge protector at the entry point of your home or of your house, and then make it in a way where it's a bulkhead connector, and that bulkhead connector is bonded directly to ground. So you're kind of like taking in both. You're grounding the shield at the same time putting a surge protection on your signal line or your center pin. You can also think of it as a surge protection device as like an equipotential device. It's like an equipotential bonding type. So you're sort of like looking at it, how do I equalize the voltages throughout my facility? And surge protection is one of those. So any electrical fault as an incidental, the only way for that is circuit breaker, surge protector device. Again, you got transients that's occurring also on your main lines. Some of them may not be as applicable on your radio facility, I guess. Some intentional sources of noise are two-way radio. that's necessary, and hum and all that stuff. So it's, again, bonding and grounding. It's pretty much, I'm sure you guys are familiar with that. So here are the typical grounding requirements for each industry or each standard. The NEC requires 25 ohms as a target. If you can't meet it, they require you just put two rods 8 feet apart and call it quits. You don't need to measure it. The military handbook requires 10 ohms to ground, 10 ohms to earth, rather. IEEE, it's all dependent on equipment. Motorola standard. This actually has changed. It was, I think they go with 10 ohms and they target 5 ohms, but 10 ohms first, 5 ohms if you can, and if you can't, do the best you can. That's kind of the thing with the Motorola and the telecommunications industry. The idea on here is to try to design in a grounding system so that you can protect your equipment at the very beginning and not do it and after the fact, because it makes it a lot more difficult to add a system when the building is there already. Now you're going to have to consider about running all this wires and all that. But if the building's not there, you can create this grounding system, the better. It'll be easier. So why do we want to have a lower resistance to earth? So here's just a simple example, a very rudimentary example. 25 ohm grounding system strikes a tower, and a potential rise around here is 450 kilovolt. So there's 450 kilovolt of voltage rise in this site. So it may be 450 here, it may be 451 here, or maybe 439, so on and so forth, and dissipate. But on the step, on a gridded or a step, voltage may reduce, but still you're seeing a big difference in voltage. At 5 ohms, you're looking at 90 kilovolts at the site. So from that perspective, I'd rather have a lower resistance to earth as best you can. Again, you can dissipate the energy to earth, back to earth, as quickly as possible. So this is best for sensitive electronic equipment, and it is best for dissipating unwanted potentials. And you can have a better reference zero for the site. And it's all depending. To try to get to 5 ohms, the size of the grounding system is very important. And as we said, a mountain site, forget it. The mountain peaks, forget it.
All you can do in that case is the bird on the wire example you suggested.
Exactly. And just create basically a ground plane, a gridded system, and then connect everything together to that system, and have radials pointing on different level, going in different direction and different lengths, so that hopefully you'll get a tuned circuit where it follows those radials. So minimizing noise is basically using the grounding, low impedance to earth, single point ground, or create a ground window. We kind of covered that earlier. Keep conductor impedances to a minimum. Ground connections as short as possible. Bends of greater than 90 degrees and 8-inch radius. Again, those are ways of minimizing those potentials from lightning. Isolation and shielding. Not much for lightning protection, but it still helps. Especially on signal lines, not necessarily for coax, but for twisted pairs, running power cables or those signal lines in ferrous conduit improves it by shielding it a little bit more. But again, if it's inductive, it's going to go through whatever it can, But having at least one layer of shield helps. So, what would it look like as far as a typical single point grounding system? Here I'm showing a typical site, communication site, not necessarily the ham radio facility that's typical. I don't have slides for that. I do apologize, but I'm hoping by presenting the concept here, you guys would be able to adapt to what you may need for your facility, for your setup. So basically, you want to have a master ground bar. So the idea here is anything within the room or anything within the immediate within the walls, you try to create a master ground bar, and you home run back to that. And I'll touch a little bit more, and I do apologize I didn't add it here on the slide, but there are standard industry standards as far as the gauge of wire relative to the distance that you run that's recommended, so you can maintain a low impedance back to earth. I can touch on that a little bit, but the idea is you have a single point ground within the room, and anything exterior pretty much goes directly down to the ring or the grounding system. So keep everything exterior. You can do multiple grounding points, but anything within the facility or within the room, make it a single point if at all possible. So that is the concept that we always use, and that is a concept that the U.S. telecommunication industry uses. The European industry uses a multi-point ground system. So they'll have multiple grounds coming in from exterior into this area. But what that does, it makes it more difficult to maintain. It makes it more difficult to trace where the possible issue, underlying issue might be, where the potentials might be coming through. With this one, it's just coming from one location, and anything that's induced within the facility will go back in here into this. So let me see here. So telco is bonded to the ground bar, main ground bar. The rack, equipment rack, we normally have insulation to isolate this. So it's really just dedicating its ground, taking its ground path this way. Yeah, one can say, okay, what about the AC ground and all that? Yeah, true, there's another path there, but as far as transients is concerned, the AC ground is more of a high impedance path because of a smaller gauge wire. So we consider them to be a high impedance path, but yes, it is still a ground path, and can also be a potential for transients to come in and disturb your equipment. So you can have a secondary ground bar and bond everything from there as well. So in the case of a Radio Shack, maybe you can have a ground bar by the radio equipment, have all of the radio equipment bonded to that, and have one heavy gauge grounding conductor going to the main ground bar or to the grounding electrode for the shack. This secondary ground bar here is basically bonding the RF SPDs that are on this coaxial cables that come in. So these are all bulkhead or maybe what we refer to the industry as chandelier, where it's basically 2 tiers and all of the SPDs are mounted on that ground bar, and they're all bonded to this secondary ground bar. Oh, I'm missing something to show how the outside shield is bonded. So actually, let's see here. No, I don't. Okay. As far as the exterior ground bar, just imagine this to be on the outside. There's another one outside. There's normally an exterior ground bar where the RF shields are bonded to that ground bar, and that ground bar is bonded straight to the ring. And that's basically the idea there is any energy that comes along the shield would be diverted back to ground via that grounding conductor. So this is a typical telecom site as far as how it's protected. We have a surge protector as well on there. I touch a little bit about distances, length of the conductor, grounding conductor relative and versus size to maintain an impedance. A number 6 wire is pretty much the smallest wire that we would normally recommend. And the distance by which that number 6 wire can, I think it's up to, I'm going blank on this one. I think it's up to 30 feet. And the number 2 wire, or no, not 30 feet. I think it's less than that. But number 2 wire, definitely a number 2 wire is up to 30 feet. And then, and so on and so forth. I can send you the table on that one, Clint, and you can probably provide that to the rest of the group.
Okay.
Because I think that will be useful. I know a lot of recommendations is to use
I've seen copper strap used.
Copper straps.
Yes.
But sometimes it's not practical. So what's most practical in the industry is using the just normal conductor, but size it accordingly.
Right.
So, let me see here. So the benefits of a properly designed grounding system: you get predictable results, improved personal safety, improve reliability, improve equipment performance, improve power quality to some degree. The biggest one is in the industry, as far as commercial side, the manufacturer's warranty requirements are met, because a lot of them, they want proper grounding for them to warrant their equipment. Oh, let's see here. Was I supposed? That was not supposed to be there. I can cover this on another.
What we're starting to run long, so I'll leave it at your discretion to wrap up.
I'll end it here. That's not supposed to be here anyway, so I'll end it here. So as a summary, grounding is a foundation for personal safety and system performance. Low impedance to earth with a single point grounding minimizes potentials in the event of lightning, fault, or heavy load switching. A good single point grounding system implementation always starts at the design phase, so resistivity testing is a key variable for grounding design. Effective pragmatic economically sound earth resistance targets is engineered using computer-aided grounding design software. Test the system before commissioning is another thing, just to know where you stand. And then you can monitor the grounding system through its life cycle. That's basically it. Here's some of the standards that we use most often whenever we do our jobs. So it may be handy to you all.
Okay.
That table that I was referring to, as far as wire conductor size versus length, can be found in 419, but I'll send that to you.
Okay, excellent. I'll include that in the show notes, as it were. Yes,
absolutely. So that's it.
All right. Let's see. So if you can unshare. I think I was making notes as you were talking, but you summarily slayed every one of my points. So.
Oh, okay.
You've given this presentation before and certainly know your way around it. I guess, in short, people will look at this and seem overwhelmed, perhaps, that, oh, I didn't do any of that. But the thing is for heck's sake, put as good a ground system as you can, as near as the entry point, and tie stuff together. If you had to do some takeaways, is that mostly it?
That's basically it. Tie them all together as best you can.
Preferably tie them together outside the structure.
Correct, outside the structure. And if you ever put a lightning protection system, make sure they're all bonded together, and
yes.
and make as many down conductor paths as you can for the lightning protection system. So it's just the concept is you're dividing it in a smaller and smaller voltage on each path.
Yep.
Yeah, as you divide that, less induction, less voltage, less ground potential rise.
Plus, this is something that gets installed and forgotten about. So the more connections you have, the fewer of them are likely to be shot when something actually happens.
Right. Yeah, with the grounding system, it's more of like bury and forget it. That's pretty much it. But please don't forget it because it's important.
Right. All right. Well, I thank you, and I think we'll call it good at this point.
All right.
Thank you very much for taking the time, Larry. And this is one of the better, more thorough lightning protection presentations I've seen, but I'm sort of a nerd when it comes to this, so, sort of thing. So I do appreciate it, and thank you for once again.
Thank you much. I appreciate it.
All right, thanks. As I mentioned, this recording was made before the meeting, so we can't take live questions, but we'll do the best we can if you do have something that came up. In the meantime, Morris, wake you up again. Remind us about the upcoming classes while people get any questions together that they might do.
Okay, well, I do have one question that wasn't quite clear to me, or maybe I just didn't hear him correctly. We talk about, was it Nalox or that material to help prevent two different metals from corroding one another.
Right.
Was that a good idea or not a good idea in a bonding system?
Well, I think it's a good idea, but his concern was that if you have dissimilar metals like aluminum and steel or copper and steel, when there's moisture involved, you're in danger unless you bond it with an interstitial metal or catweld it, at least from a lightning standpoint. Inside a building, it should be okay. I think one of the takeaways would be with that in mind, you do the best you can with what you got, which is better than doing nothing, and you keep an eye on it. But he did also point out, too, that stainless steel hardware seems to be fine. Stainless steel seems to be a reasonable choice for an interstitial metal to go between, say, galvanized tower and copper. And of course, gooping it up with whatever just will always keep the moisture off it. That's never a bad idea anyway. So does that answer kind of what your thing was?
Yeah. I have my lightning arresters are mounted on a quarter-inch thick plate of copper, and then I have an aluminum L bracket that mounts that to the back of my NEMA box. Okay.
Yeah, he seemed to shy away from aluminum connecting to anything other than some sort of intermediate metal. Now, one question that would have been good to ask him was, how good is stainless against aluminum?
The takeaway I got on the Nalox was it's okay if it's used in a dry location.
Right. So if you can keep it dry and it's all gooped up and all that,
inside the NEMA box, it's pretty dry.
Right. Interestingly, he did point out that these days most lightning systems are mostly aluminum, which kind of makes sense from an economic standpoint. But I guess aluminum is fine as long as you know what you're connecting it to and how to make sure whatever you connect it to isn't going to rot itself to pieces.
Yeah, my memory is that at Leamington, there is like a 1/4 inch or 3/16 inch strap of a thick strap of copper running all the way around the room on both inside and outside of the wall.
Yeah, I think he didn't talk about it, but I believe that's referred to as the halo ground, which is just the ring ground, except it's up in the air. It would be interesting to know, maybe there are some slide drawings, to know whether or not Leamington has ring ground in the ground. I'll bet it does, but the philosophy of lightning protection has changed in the past couple decades. So obviously that site, whatever they're doing there, seems to be working fine, since nothing has gotten the daylights blown out of it in the past 50 years.
Yeah, I know that Steve has said that the tower has been hit by lightning while they were inside the building watching television and didn't even get a blip on the screen. So
Yeah.
that's pretty good lightning protection as far as I'm concerned.
Now,
a couple of questions from you.
Go ahead.
Both from Ron Jones. One was, would he be available to do a similar presentation for one of our groups here in Arizona?
Well,
They get nasty lightning down there for sure.
well,
And
yeah.
the second one is, do the chemical grounds have a finite life?
Well, like anything, you got to do maintenance on it. I mean, he said more than once, you don't put it in and forget it, although that's what happens, which is one of the reasons why he said run multiple down leads and do lots of ground rods, because inevitably you do forget it or things corrode, and having more of them will hopefully make sure that more than one will work. Now, as far as having him there for a club meeting, have Ron contact me, and I'll try to put you in touch with Larry and see what he says. So we can try that.
I know Kessler Peak, we just put regular table salt, 5 pounds around each ground radial, and it took a couple of years, and it significantly improved the ground.
Right. And what I have personally done is I've used magnesium sulfate, aka Epsom salt, which is fine if you have vegetation around, but if you don't have vegetation around and nor aquatic life, then copper sulfate apparently works too. But one thing he did caution about it is you don't want to salt the earth so much that you corrode everything inside. He did kind of talk about that XIT ground, which is what he did let on was that since the patents are expired, you can probably, since they're patented, you can probably look at it. Apparently that's some sort of calcium-based salt, and I'm presuming that it's easier on the metal than other things. But in this area, even just a little bit of salt in the ground, or salt of some kind, there are many types of salt, would probably go a long ways to improving things, especially if you live in kind of sandy or clay soil. Let's see, any other questions?
Nothing's popped up here.
All right.
So to answer your original question, we will be teaching for sure a technician and a general class starting the week after the UARC meeting in January.
Okay.
If COVID conditions are good enough, then we will have an extra class also. Right,
and I take it the extra class is too involved to comfortably do via Zoom. Is that your concern?
Well, it's not my concern. Ron teaches a little over half of that class, and he's just unwilling to do it online.
I got you. Okay. All right. Well, thanks for the update. Let's see. Let's wake somebody up here. What is December's meeting besides elections? Does anyone have that at hand right now that they can say? What's upcoming for the December meeting?
It's station evaluation.
Oh, this is for the new RF exposure stuff, isn't it?
Right.
Okay, and as a summary, if you've been following any of the news, the FCC is now requiring that you at least evaluate your station to see if it is safe in terms of RF exposure. Now, this isn't nearly as difficult as one might think. If you're running below a certain power level and certain frequencies, all you need to do is say, yep, I'm fine. But if you're running high power or indoor antennas or something like that, you might want to at least do some of this cursory look at stuff. And I believe that'll be what, Paul AE4KR that's doing that. Is that right?
I can't remember his call sign. Flat.
Okay.
Paul.
Yeah, that's Paul Plack, AE4KR.
Yeah.
So we'll be doing that in addition to elections. And by the way, the elections this year will be done the same way as last year. It'll be kind of done by acclamation on Zoom. So
unless we get a swarm of people saying we really want to run.
Right, that's true.
But they will have to have notified us. Let's set that by the 1st of December.
Okay. So if you are interested in running for a club office, any club office, let us know by the 1st of December, and we will add that to our slate of candidates. Clearly, we've had to modify the bylaws of the club, which stipulate an in-person meeting or something, which isn't necessarily safe. Although we are continuing to reevaluate that, whether or not we want to do an in-person meeting. And when we do an in-person meeting, we will do our darndest to make sure that we can make these meetings occur live on the web as well. So we still have our eyes on doing that. Any other final business before we wrap it up for the evening? I'm hearing nothing. I don't have a cricket sound effect. So I thank everyone for showing up, and we hope to see you again. And make sure you watch this in a replay if you missed anything. So 7-3, take care.
Thank you.